Hey everybody, welcome back to another AP Precalculus video. Today we're going to be doing 1.5 polynomial functions and complex zeros, and this is going to be part 1 of our 1.5 unit. 1.5 is a really big unit with a lot of important concepts, so we're going to be splitting it into 2 parts to make sure we get these concepts down one at a time. So right here, we've listed all of the topics we're going to be covering in this part 1 video, and part 2, once it's out, will be linked in the description below, so you can go check that out afterwards. So we're going to be going over zeros of a polynomial functions. We're going to be going over factors, degrees, intermediate value theorem, and non-real zeros and their conjugates. That all has to do with the zeros of our polynomial functions. And we're also going to be going over multiplicities, so talking about if they're even or odd and how to find these multiplicities. And then lastly, we're going to be talking about finding equations from zeros. And of course, we're going to have examples at the end. All right, so these are all the learning objectives for 1.5. And again, the last slide is just what we're going over in this video, and then we will go over the rest in the next video. All right, so our first topic for today is zeros of a polynomial function. Now, a zero of a polynomial function is the x-intercept of that function, or the value of x when y equals 0. Now, the degree, which we talked about in our last video, it's the highest power in which x is raised. The degree of our polynomial function can tell us the maximum amount of zeros the function contains. And the maximum number of terms that a function has is 1 less than the degree. Now, these are going to be important later on when we start actually sketching out graphs based on a given polynomial function, but just keep that in mind for now, and we're going to do some practice with it later on. So let's take a look at the degree here and see what information it tells us. So h of x is our polynomial function, and 5 is the largest exponent to which x is raised to, therefore it's the degree. So that means that the maximum number of zeros h of x could have is 5. It's equal to our degree, and the maximum number of terms is 1 less than our degree. So 4 would be our maximum number of terms that h of x could have. Now, it could have less, but this is the limit to it. All right, zeros of a polynomial function can be found from factors. So if you factor out polynomial function, you'll end up with binomials, and generally in this form, x minus b x plus c, and the opposite of these values right here, so in this case, negative b and positive c, the zeros will be the opposite values. You can think of it like that. So x will equal to b and x will equal to c. If you plug b minus b, you get 0. If you plug negative c plus c, you get 0. So that's how that works. But we do have a little example right here just to show that. X squared minus 5x plus 6. You can factor into these binomials. And then finding the opposites of these values, negative 2, negative 3, would be 2 and 3, which is our zeros. So the function crosses the x-axis at x equals 2 and x equals 3. That's when our output values are 0. All right, next we're going to be going over intermediate value theorem. And this is just the idea in which if a function's y value, output value, switches from positive or negative to positive, either one, there must be at least one zero. Now, on this graph right here, the y values change from 1 to negative 1. It changed from positive to negative, so there must be at least one zero. Now, right here, there's a 0. It crosses that x-axis. And this same thing happens vice versa. Negative 1 to 1 again, it switches from negative to positive. So we know that there's going to be a 0, and there is indeed a 0 right there. So this is just showing how the intermediate value theorem works. You can also call it IVT. And IVT can also be seen from tables. So right here, we're given g of x, output values, and corresponding input values. So if you notice right here, it goes from 7 to, so we're still positive, to negative 12, so it switches from positive to negative, and then negative 12 to 9, it switches from negative to positive. So we know that between negative 5, negative 6, and then negative 6, negative 7, there's going to be some zeros. So there's going to be 1 between negative 5, negative 6, and 1 between negative 6, negative 7, because their corresponding output values switch from positive to negative, and negative to positive. All right, so we're going to have a quick conjugate review, and this is going to be important for our next slide. So conjugate is basically flipping the sign between the terms in a binomial. So 2 plus x would be 2 minus x, and x minus 3 would be x plus 3. So the conjugate of x minus 3 is x plus 3. Conjugate of 2 plus x is 2 minus x. We're just flipping those symbols. And this is going to be important because we're going to talk about non-real zeros. Non-real zeros will be in the form of a plus bi. Now, if a plus bi is 0 of our polynomial function, know that its conjugate, so flipping the sign, a minus bi, will also be a 0 for that polynomial function. So for instance, if 3 plus 5i was a non-zero, that function would also have 3 minus 5i as also a 0. All right, next we're talking about multiplicities. Multiplicities is the number of times a particular zero appears. You can also think of it as the number in which a factor will be raised to. Because again, the factors will tell us what a zero is on a function. So right here, x minus 2 squared. Now the 0 right here is 2. You take the opposite of negative 2, it's just 2. And it's squared, which means it shows up twice. And we can see this if we rewrite it as x minus 2, x minus 2. You're just multiplying this factor twice. That's what that squared means. And these multiplicities are going to be really important for sketching out graphs, and here's why. We're going to want to look out for even and odd multiplicities. All right, so even multiplicities, 2, 4, 6, 8, so on, all our even numbers will touch the x-axis and then change direction. So you can think of it as a bounce. G of x equals x squared. Our x will be at 0. There is an even multiplicity. This x is raised to 2. And since it's even, at x equals 0, our graph is going to bounce. So this is the g of x graphed out, and you can see that it goes down, it touches x equals 0. It's still a 0, but it doesn't cross the x-axis. Instead, it bounces up and changes direction. It goes from decreasing to increasing. So that demonstrates kind of how even multiplicities will work on a graph. Now, in contrast, if you look at odd multiplicities, these will cross the x-axis. So x to the power of 3, our 0 would be x equals 0. That's where y is 0. And the odd multiplicity will make it cross the x-axis. It'll keep going the same direction. We're increasing, and after it crosses that 0, we're still increasing because it crosses the x-axis. So odd multiplicities will cross, even multiplicities will bounce. All right, and lastly, we're going to be looking at finding equations from zeros. Sometimes you'll be given zeros of a function, and you're going to be giving multiplicities and coefficients. We're going to be using all these elements to find the equation for h of x. These zeros can be made into factors, into these binomials. You have x equals negative 2, x equals 3. Take the opposites of these x values, you get x plus 2, x minus 3. And since this 0 right here has a multiplicity of 2, we're going to raise this binomial to the second power. All right, and we're going to have a coefficient of 3, so we're just going to put that right in front, and we're going to be multiplying all of this together. So you distribute like so, and then you get h of x equals 3x cubed minus 12x squared minus 9x plus 54. That would be the equation for h of x based on this given information. All right, so we're going to be moving on to examples, and we're going to be going over examples of each topic we covered today in this video. First, we're going to be using the degree to find information on zeros and terns. So we want to identify the degree first. You can pause the video to try out these examples yourselves. So 700x to the power of 13 plus 1x plus 9x. The degree would be 13. All right, so maximum number of zeros would also be 13. It would be equal to our degree. And then the maximum number of terns is 1 less than the degree. So it would be 12 terns. Second example, factoring to find zeros. So you want to factor 9 plus 12x plus 3x squared. So first we take out that GCF, greatest common factor, and then you just factor like normal. So you get 3, and then you get these binomials, x plus 3, x plus 1. The opposite of these values right here in our binomial will be our zeros. So our zeros would be x equals -3, and x equals -1. Because when you plug these in, you get 0. All right, we're going to be looking at the IVT, intermediate value theorem. Again, that's when our output value switches from positive to negative or negative to positive, which tells us there will be a 0. So you have g of x and x. So let's take a look at when the graph switches from positive to negative or negative to positive. 500 to -600. So we're switching signs. -600, negative 0.001, or signs stay the same. And then negative 0.001 to 1, sign switch. So since it switches twice, we will know we'll be having at least 2 zeros present in g of x just based on this graph. Now, within which intervals will these zeros occur? So since 500 and -600 are our output values for these input values, 1 and -17, d0 will be between -17 and 1. And this also applies for these values right here, since we're switching again. So it'll be also between -200 and -20. Smallest values go first. So these are intervals in which our zeros would occur. All right, we're going to be talking about non-real zeros next. If function h of x has a non-real zero of 4 minus 22i, what would another zero of h of x be? So we're going to be thinking about our conjugates, in which the signs of our binomials switch. So right here we have a minus 4 minus 22i. So 4 plus 22i would be the other non-real zero of h of x. All right, we're going to be finding multiplicities of our function. So to find the multiplicity, we want to factor out this function into binomials. 2x squared plus 2x minus 4. So once you factor it all out, this is what you're given. This 0 would be x equals 1, and this 0 would be x equals -2. And so since they're both raised to the first power, that means these zeros are going to appear once, which means they have multiplicity of 1. Next, we're going to be doing more multiplicity practice, except this time we want to notice if they're even or odd. So right here, j of x is already factored out for us. Our 0 here would be x equals 2, and since it's raised to the third power, our multiplicity would be 3 at x equals 2. And it's odd. Right here, x equals -8, and it's raised to the second power, it's even. All right, next we have x minus 21 to the power of 69. So our 0 for this binomial right here is going to be x equals 21, the opposite of -21. And then we're going to raise it to 69, which is an odd number. So it's going to have a multiplicity of 69, which is odd. And then finally, our 0 for this would be x equals 0.5. And since we're raising it to the 26th, our multiplicity is therefore 26, which is even. All right, so how does this apply to our graphs? How do even and odd multiplicities apply to our graphs? So it's going to talk about if our graph crosses the x-axis at the 0 or bounces it. Again, if it's even, it'll bounce, and if it's odd, it'll cross. So right here, we have this graph, and we have zeros at -1, 0, and 1, because that's when it's touching this x-axis. So right here at -1, it bounces. Our function goes down, bounces, then goes up, decreases, bounces, increases. So therefore, this 0 will have an even multiplicity. All right, and then at zeros, x equals 0 and x equals 1, we're crossing the x-axis. We're still going in the same direction. So from here to here, we're decreasing still, and from here to here, we're still increasing. So that's where we're going to have our odd multiplicities. All right, and here's another example of that for extra practice. First, our zeros, we're going to identify them, 2 and 3 and 4. So right here, we change direction, decreasing to increasing, it bounces, it does not cross. X equals 2 is going to be a 0 with an even multiplicity. And then the other two would be odd multiplicities because we're crossing the x-axis. All right, this is our very last example. Find the equation of h of x if it has these following properties. So a 0 at x equals 2, 0 at x equals 3, and this 0 has a multiplicity of 2 and a coefficient of 2. So we're going to set up h of x. We're going to have our coefficient of 2, our zeros, which are binomials. So since it's 2 and 3, it would be x minus 2, x minus 3, and then our multiplicity of 2 at x minus 3. So we're going to raise this binomial to the second power. All right, and then now we just distribute. So we're just going to do our simple algebra. Spread this 3 into x minus 3 times x minus 3, and then distribute like normal. And once you do that, you get 2x to the third power minus 16x squared plus 42x minus 36, and that would be the equation of h of x. All right, so that is it for 1.5 polynomial functions and complex zeros, part 1. So this isn't everything in 1.5. Thank you so much for watching, and stay tuned for more AP Precalculus math lessons. 1.5 part 2, if you're looking for some of these topics that we didn't cover yet, the part 2 will be in the description box below. And thank you again. Bye!